Welcome to the T-Navigator Knowledge Series. This series is designed to provide an in-depth look at how the T-Navigator software is transforming the way the energy sector approaches complex simulations. Each episode that we'll go through in this T-Navigator Knowledge Series dives into a specific feature of the platform, showing you how to maximize its potential. Whether you're optimizing oil production, driving clean energy innovation, or advancing carbon capture and storage projects, you'll find the tools and insights you need right here.
Welcome everyone to this installment of the T-Navigator 1 Knowledge Series. Today we'll be going through a carbon storage case study performed in T-Navigator. It's called Integrated Modeling and Target Selection for CO2 Storage. So we'll start with just a bit of a background on the data set we're going to be using. This is the Schmiahead data set from the North Sea. And this is provided by Equinor and Gas Nova. It's an open data set and can be found on co2datashare.org. The data provided includes 3D seismic data, interpretation such as faults and horizons. There are 2 wells with all the time logs required, raw and petrophysical logs, markers and drilling reports, as well as some geomechanical data. There's pressure and temperature data as well. They've also provided 2D seismic throughout the area. When this project was originally done, that 2D seismic was not available, but now for anyone who wants to access this data, it's there, so you can actually do quite a large basin study using that. Now, the formations of interest, we're going to be looking at the Dropney Formation as the seal, so that's a regional marine mudstone, very important as a trap throughout the region. The reservoir will be focusing on the Sognefjord and Fensfjord formations. These are deltaic shallow marine sandstone deposits of very high porosity, and they're saline aquifers, so there's no hydrocarbon to worry about in this case. The scope of this project, we'll be looking at building a static model integrating seismic and well data. So to do that, we're going to bring the time data to depth, and then we're going to build our structural model integrating that fault data with the horizon data. And then we're going to distribute properties from petrophysics. Now, the issue being there, we only have 2 wells, so we need to find a way to do this in a geologically meaningful way. From there, we're going to look for a target to inject CO2, and we're going to keep in mind some common storage risk criteria specific to this project. Following that, we're going to simulate CO2 injection within the target area over 100 years to see the effects of storage mechanics in this model. And then we're going to look at the impacts of different subsurface criteria on CO2 storage through a simple uncertainty study. So we'll just talk quickly about some common risk criteria for CCS projects, right? So if we break this into 4 different groups, right, we're looking at capacity, injectivity, containment, and then social and economic factors. So if we're thinking about capacity, we're looking for a thick, clean, high porosity reservoir to be able to inject in so we can hold a lot of volume of CO2. Obviously, higher porosity or higher pore volume is going to give us higher storage capacity. Next, looking at injectivity, so that's reservoir quality. So we're looking for high permeability, lateral and vertical continuity of high permeability facies. And then we're trying to consider any pressure limitations on the injection rate as well. For containment, so we need a suitable trap or seal. Presence of faults, that could be an issue for containment, such as sealing or non-sealing faults, areas for migration, reactivation. So that falls right into stresses and geomechanical considerations as well, which does go back into pressure limitations. Depth to remain in a supercritical state. So we need to be deep enough that we're not going to leave that supercritical state during injection. Dynamic trapping mechanisms. So we're looking at residual dissolution, mineralization, things like that. And of course, proximity to producing fields, right? Obviously, everywhere there's an existing well penetrations, that's going to be an issue or potential risk for injection. And then on the social and economic side, people will consider things like tax structures for the area you're in, the purity of the CO2 you're injecting, distance from the source of the sink. So building that pipeline to get that CO2 to wherever you want to inject it is one of the most expensive parts of these projects. So you need to consider where you're actually doing this. Proximity to populated areas, that's more of a PR concern. And then, of course, proximity to underground sources of drinking water. A lot of protection around that, so you need to be mindful of that. And then any other permitting requirements for the area you're working in. For this project, we're going to be ignoring anything past this red line, right? So we're really just looking at capacity, injectivity, and containment. And we know we don't have any producing fields or existing well penetrations besides the two we're looking at here, so not a lot of risk there. And then, since we're looking at static and dynamic modeling, I've just colored these tasks based on what we might do in the static model versus what we might do in the dynamic model, right? So if we're working in T-Navigator to build this static model, we need to consider what can we actually do to build that model. And we can pretty much do everything required, right? Well, from bringing in the data and QCing it through geophysical interpretation, geological interpretation, and then into, of course, building our actual structural model, right? So building that geocellular model, incorporating faults and horizons to represent the subsurface, and then property modeling, right? We need to distribute all of our properties through the model, and then of course volumetrics and uncertainty, which we'll get into following that. If we're looking at first bringing in our seismic data, all of the seismic data that they provide here is in time. So we need to bring it into the depth domain. So first we're going to do some quick seismic well tie on those two wells. And with the time logs available, it's pretty straightforward to do that. And then a simple velocity model was constructed, right? It's just a basic interval velocity model. And what we've done is we've shifted all of the time surfaces to depth, and we've also shifted the fault interpretation into the depth domain as well. So now we have that seismic data as well as the data from wells to build our structural model. So going into structural modeling, we start with fault QC, right? So when we have our faults, maybe they're not always the cleanest coming from seismic data, but we can use the tools in T-Navigator to start editing those faults, whether manually, individually, or using our fault QC tool where we can see fault relationships, see where they're crossing, where they're bent, where there might be some issues with them. So let's say we have some crossing faults and we need to perform some truncations. We can do that easily using this tool, right? Where we can click on one of the fault pairs, see the relationship, and generate a new fault truncated where the minor is truncated by the major. And then once those are all prepared and ready to go, so let's say we've got our faults edited, we set up our horizon relationships to see the displacement we want on our faults, we can move into the grid construction phase. So if we look at that, in this case, what we did is we used points from horizons, so that's from seismic interpretation. We used the well tops, and we used the faults to generate this grid. And what we've done is we've made a basic pillar grid where we have some faults that are true pillars, those are called structural faults in T-Navigator, and some faults are stair step just to deal with higher complexity situations. And we ended up with our main zones, right? So we have our Dropney and our thinner heather zone as our seal. Then our main reservoir zone is the Sognefjord and Fensfjord, and then the Crossfjord at the bottom, which is really ignored for the purposes of this project, but it is a potential injection target as well. And we ended up with a block count of around 3.6 million cells, so a larger model for the simulation side of this. Now moving into property modeling. So we wanted to find a way to, distribute the porosity, right? So we wanted to bias that to facies, but we wanted to find a method, something from seismic as well to help distribute this data. So in general, when there's no hydrocarbon in the formation, we can usually find a decent relationship between RMS amplitudes and porosity, where if RMS amplitudes are increasing, we'd expect porosity in a saline aquifer to increase as well. And so where we have that happening, we would expect more sandstone. Now, if we look at a cross plot of RMS amplitude versus phi E, which is all provided, well, the RMS amplitude was extracted using our attributes calculations in T-Navigator. We can see there's a relationship, and a stronger relationship, of course, in the sandstone facies. So here we just did a simple mudstone sandstone facies pick in the two wells. There are a couple of cases where we have some low porosity, sandstone, and there are cements present in the formation. So that's how we're accounting for that. But we overall we see a decent coefficient. Um, Again, as I mentioned, a better relationship between the sandstone facies and RMS, and we can use this to help guide the distribution of our both our facies and our porosity. So if we look at that, right, we're looking at our input data, which is going to be well data. So it's going to be our log data. We have our facies log, our porosity log, and we have seismic data. Now, first, the facies model was made. Again, just a simple sandstone, mudstone model. You can see, our top seal is all mudstone. What was used in T-Navigator is a custom algorithm called Amazonas. This is rooted in machine learning. It's, in this case, an unbiased mode distribution. And we fed it zonal maps, zonal RMS maps, to help guide the distribution of that sandstone. Following that, we use that facies model as well as an upscaled RMS amplitude volume. So we've taken the actual seismic cube, upscaled it into the model. We're going to use both of these to guide the distribution of our porosity. So it's biased to sandstone and mudstone. So where we have sandstone, we would expect obviously the distribution of our higher porosities. And where we have higher RMS amplitude values, we're again expecting distribution of higher porosity values. And this was done using just stochastic Gaussian simulation. So a very classic geostatistical distribution. Following the creation of the porosity model, a permeability property was extracted using just a simple function. This was provided in the existing model that Equinor had created, where they already have a porosity and a permeability property. So what was done in this case is that same function was just typed into our calculator, and we backed out permeability from porosity. All right, so we have our general static properties created or calculated, and the rest of the properties, such as geomechanical properties, those are just coming from reports that they have provided in this case. So just general zonal values, bulk zone values throughout. But next we want to look at injection target selection. So we're going to look at a couple things. We're going to look at containment risk and then capacity. So for containment risk, the three main criteria we considered were caprock thickness, depth to the top of the reservoir, and distance from faults. Caprock thickness was over 25 meters everywhere, so we really considered it a non-risk. Obviously, you'd want to do more caprock integrity analysis for an actual project you're going to move forward with. Depth to the top of the reservoir, so we really wanted anything greater than 900 meters. This is kind of a rule of thumb, greater than 800 and 900 meters depth to make sure you're at a supercritical state when you're injecting. And really the only issue area was at the northern top corner. And then, of course, probably the biggest issue in this area is distance from faults. So you could probably, in reality, just make this distance from fault maps to map to consider where you want to inject. But for the purposes of this project, we'll continue forward just to see the whole process work through. But you can see this area between the wells is going to be probably our best area to inject. Okay, so if we're looking at capacity and injectivity as well, we considered our porosity. So obviously, like I said, we want higher pore volume. So we're just looking at a map of phi H, which would correspond to the ability to inject that CO2. For injectivity, we want more permeability and we want more continuity. So where we have higher average perm, we're going to expect higher injectivity. And then we're looking at if we look at a layer count of low permeability layers, we would expect where there's higher or lower count of layers, we have greater vertical continuity of sandstones. So that's going to be a better target for injection as well. If we put all these maps together just to make a chance of success map, so what was done here is the product of the risk maps was taken and multiplied by the sum of the capacity maps, just so that we aren't being overweighting those capacity maps, because they're not necessarily an ender or killer of where we might be able to inject, right? It's still decent porosity and good permeability everywhere, but we still want to see where that impact is. But we want to still be able to have those risk maps have a larger impact. So you can really see, obviously, where there are faults that has the greatest impact, where we're too shallow, it has a great impact. And we end up with this injector here, what looks like the best region to inject. If we look at A to A prime, this is just a slice through. Here we see our zones and our porosity. And, as expected, our Sognefjord has the best porosity, it's the best reservoir, and the top of the zone is where we'd expect the best injectivity to be. Okay, if we move into the simulation phase of this project, right, so we're going to be injecting CO2 into water zones. So we're going to be looking at CO2 solubility into brine, as well as structural trapping as the major mechanisms for sequestering the CO2. And like I mentioned, it's nearly 3.6 million cells, so it's a pretty big model for simulation. We're going to inject CO2 over 100 years. So the injection phase will be over the first 30 years, and then it'll just be monitoring over the remaining 70 years. If we're looking at the simulation mechanisms for CCS in T-Navigator, and we're going to be considering structural and stratigraphic trapping. So that's a function of our grid structure and our static properties. Residual trapping. So we'll need to model capillary pressure or hysteresis saturation. And we'll note that the CO2 becomes isolated during plume migration. We'll also have to consider dissolution and mineralization. So we're going to look at CO2 dissolving into the fluid, in this case water, and denser CO2 rich water will tend to sink to the bottom. We'll also look at mineralization. We consider that during simulation. And, so where we see CO2 reacting with salts in solution or with other rocks, we will see mineralization related to that. And then we also run geomechanics coupled with the fluid simulation. And so not just considering, the integrity of the reservoir, but also its effects on reservoir properties, right? So, we consider the cap rock and reservoir integrity, but we will see maybe changes in porosity and permeability related to changes in stress. And we can also flag potential displacement as an effect of geomechanical simulation. So we have several options for the simulation of CO2 injection. In this case, we're considering CO2 store. This would be the most common option used for injecting into a saline aquifer, and it's one of the most simple for this case, so it's an excellent candidate for this project. Now, if we compare our estimated plume, which was this blue circle originally looked at, versus the simulated extents, you can see we actually ended up with a much larger plume than expected. And this is likely because, well, as we'll see, where the plume is migrating to begin with during injection. So the purple is the first 30 years during the main injection period. And then we can see over the remainder of time, the plume does continue to migrate after injection. So for these next slides, we'll be looking at the slice B to B prime through the injector and the plume. Okay, so first looking at structural and residual trapping. So we do see migration up dip in general, and also we do see that where we had that highest permeability and porosity layer at the top of the Sognefjord, that's where we see the most migration to begin with, right? So that's where the bulk of our plume is injected. Overall, the top seal does a good job of holding this plume in place. And we also notice that the remainder of the CO2 saturation is highest near the wellbore, right? And so that's an effect of just those capillary pressures holding that plume close to the wellbore. If we're looking at dissolution, so now we're looking at the molar fraction of CO2 in water. So the CO2 dissolves in as much water as it contacts. So once it reaches maximum solubility, that's all the red region of this plume. That's for the bulk of the CO2 plume, which is what we would expect. But then we start to see gravity segregation, right? So we see that as this CO2 rich water becomes more dense, it starts to drop below. So that's why we're seeing these colored blocks below the plume. So that's the gravity segregation and the CO2 dropping down below the plume, the CO2 rich water. Now, during the geomechanics run, we looked at just specifically any potential displacement. And if you look at the legend, the displacement we're measuring here is very small, into the fractions of centimeters. Um, and you can see where there's positive displacement and where there's negative displacement. So positive displacement, that's the hot colors. Negative displacement, that's the cold colors. Overall, like I said, not excessive displacement shown at the top seal, which is ideal. It's generally around the plume, and the highest displacement is occurring during the actual injection period because that's when the pressure is going to be the highest. You can see when we move to the 100-year injection slice, the overall displacement is much lower, so it's dropping down over time. We do see some negative displacement around these normal faults, which could be a flag for maybe we've gone over our desired injection pressure. We did pressure this up pretty high just for the purposes of this test here. And you can see even after the injection period is over, and we're just looking at migration, a lot of this displacement hangs around, this negative displacement. So it could be an issue for fault reactivation. Now, if we just watch a video of the plume growth here we can just see we're stepping through a year at a time, and we can see how that plume migrates through the model over time. So as I mentioned, we do see it migrate first and fastest at that top layer. So we kind of see that high hat shape to this plume. And then you do see those other high permeability stringers in the lower parts of the reservoir where we have CO2 migration occurring. So we can visualize this in real time if we wanted to, but typically, we would run our simulation and then look at the results afterwards and then extract our information from there. And then this is also, it can be used to measure the distance of where the plume extents are and things of that nature. Now, following this, we ran an uncertainty study, so a very simple uncertainty study where we explored 6 key variables. So the injection pressure, we applied just some simple multipliers to porosity and permeability, though we could have run multiple runs of facies models and porosity models to get a bunch of different static inputs, which we'll talk about more in a bit. We also looked at compressibility, gas relative permeability, and water relative permeability. So the Latin hypercube algorithm was used, and we just did 40 runs on our workstation. And pretty fast runs in T-Navigator, roughly 2 hours per run, which is pretty good in a model with 3.6 million cells. So what we find, if we look at the effects of the different variables, is that the injection pressure and the compressibility were the most important parameters. They had the greatest effect on the amount of CO2 we could store. So that does make sense, right? So obviously being able to apply more pressure during injection means we can get more CO2 into the formation. So a pretty wide range in how much we could store, 65 million tons to 250 million tons. If we're just, again, looking at the stored CO2 over time, you can see, there's during the injection period, and then just that level volume afterwards. And again, this is a very massive reservoir to inject in, right? So if we compare this to Whitecap's Weyburn, which is, a historical target here in Canada, they've already sequestered 36 million tons, and it still doesn't even come close to even the low end of injection potential for this one. But if we look beyond just total CO2 storage, we need to consider, the impact that other properties can have. So on things like plume shape and extents, which, many companies need to consider because they need to know where that plume goes. If it's going outside of the area they've licensed, they would need to know that, right? So what we would do is run multiple realizations where we apply variance at both the static and dynamic level, where we then would see a changing plume shape as it relates to how much CO2 we're able to inject, right? And not just related to those operational constraints such as pressure, but the actual rock itself in the reservoir that might be hindering the growth or migration of this plume. So then we can see multiple quantiles, different cases, and back those out and see what those look like in T-Navigator. Just in conclusion, so we know that Geology Designer within T-Navigator can be used to integrate data from multiple sources when constructing a complex geomodel. So we've done that. We've brought together our well data, our seismic data, and we've used attributes from seismic to help distribute the well data where we only have 2 wells. T-Navigator can be used to model all the necessary trapping mechanisms for CO2 storage, which we went through here in this case. And we know that static and dynamic properties both have an impact on determining the feasibility of injection locations. So not just the volume of storage, but where is that CO2 actually going to go? So in the end, we should always run an integrated static and dynamic ensemble. So that's where we're applying variance at both the static and dynamic level to see the effects of uncertainty on the CO2 storage and plume extents. Thank you very much for taking the time to watch this presentation. If you have any questions about anything done here, again, we're always available to be contacted on this, and this data is available for anyone else on that CO2 data share website mentioned at the beginning of this presentation. Feel free to go and download it and play with it yourself. Thank you very much.